So the build phase on Black Velvet is just about complete. I'm fine-tuning some of the last few details before I tear everything down for paint and powder coat, and I decided I wanted to give the bike a different stance with some longer forks. So I disassembled the front end and reassembled it with longer fork tubes, and when I put the front end assembly back on the bike, I could tell instantly that was the right move. The bike had the right stance, the right profile, and I was really happy with the way it looked. But arbitrarily changing the length of the front end really raises the question, how do I know the bike is safe? How do I know it's going to handle the way it's supposed to? And the answer comes from an understanding of rake and trail. So that's what I want to discuss in today's video. Now, you probably thought you could forget all that garbage they taught you in your high school math classes, right? Now let's start with some definitions. I made a sketch of a generic motorcycle chassis to help visualize some of these concepts. The rake is simply the angle of the front end, and you can see the rake of the frame shown here. Remember that rake is measured from the vertical out. It's not measured from the horizontal down. That's actually important, and we're going to need to know that later. The total rake refers to the angle of the front forks, and more often than not, the forks will have the same rake angle as the steering head of the frame. That's because most generic off-the-shelf triple trees used on mass-produced bikes don't have any angular offset to them. There are some manufacturers producing something called raked triple trees that do have an angular offset to them. They hold the forks at a different angle of the frame because they add additional rake without changing the angle of the steering head. We're going to put a pin in that for now because we'll talk about those a little later in the video. If I take the lines forming the rake angle of the frame and extend them to the ground, I get a right triangle defined by point O, the origin, point S for steering head, and point C for chassis. This angle here is 90 degrees, and angle R is my rake angle, which means angle G, where the steering head axis meets the ground, is 180 minus 90 minus R. But before we get too far into the math, let's discuss trail and how it directly affects the amount of leverage the road has on your front wheel. Looking at that same triangle, I'm going to draw a vertical line through the axle of the front wheel and mark a point on the ground that I'll call W for wheel. This is where the tire makes contact with the ground. More specifically, W is the centroid of the tire's contact patch, and for our purposes, you can think of it as the single point where the tire touches the road. Simply put, in order for a rolling wheel to be stable, it needs to sit behind its pivot axis. In other words, the wheel needs to trail the steering head axis. This is because of something known as the caster effect. Shifting our perspective to a bird's eye view, as in the camera is directly above the wheel looking down at the ground, we can see point W sits behind point S. If you imagine the wheel rolling forward and I turn the handlebars to the left, the wheel will follow a trajectory to the left. That's because the force of friction between the tire and the road is pushing the wheel to the left. Now remember that leverage, or torque, is the ability to cause an object to rotate around an axis, and it's measured by the amount of force in a given direction multiplied by the distance between the force and the axis of rotation. The leftward force from the road acts at a distance from point S, creating a clockwise torque. So initially, I created a counterclockwise torque by turning the handlebars to the left, and in response, the road creates a clockwise torque that attempts to return the wheel to its original position. That's the very definition of stability. If, on the other hand, the wheel sat in front of the pivot axis, as shown here, turning the handlebars to the left would still produce a leftward force, but that force would create a counterclockwise torque that would attempt to turn the wheel further to the left, creating a larger frictional force and subsequently a larger counterclockwise torque. And you can see how the problem would snowball from there, making a configuration like this extremely unstable. Now, the smaller the trail, the less leverage the road has on the front wheel, making the front end more responsive to the rider's input. Sport bikes and racing bikes tend to be set up with small amounts of trail that allow the bike to whip back and forth from one corner to the next with minimal effort. But trail that's too small results in the front wheel being squirrely, and in some cases could result in a wobble that's actually unrecoverable. Now, on the other hand, the larger the trail and the more leverage the road has on the wheel, the more stable the bike is in the straightaways, particularly at high speeds. But a trail figure that's too large will result in a front end that feels heavy and unresponsive. And in extreme cases, if you go to turn the handlebars on the bike, you could end up flopping the rest of the bike over, and that's bad. So there's no one universal trail figure that's right for everyone, but there is an acceptable range. And within that range, the right trail for you depends on the type of riding that you're doing. So that brings up two specific questions. Number one, what is the acceptable range of trail? And number two, how do we determine the trail figure on our own bike? Let's get the math out of the way first. Now, if you've forgotten how to calculate all the parts of a right triangle from your trigonometry classes, I'm going to give you a 10 to 20 second crash course as a refresher. You'll need to know the acronym SOHCAHTOA. There are a number of different mnemonic devices for remembering these three groups of three letters, and one of the more memorable for me is some old hippie caught another hippie tripping on acid. It's not dumb if it works. This acronym describes the relationships between the sides and the angles of a right triangle with the sine, cosine, and tangent functions. You can find the sine, cosine, or tangent of an angle simply by putting it into a calculator. SOH reminds us that the sine of an angle is the length of the opposite side divided by the length of the hypotenuse. CAH means the cosine of an angle is the adjacent side divided by the hypotenuse, and TOA means the tangent of an angle is the opposite side divided by the adjacent side. And that's trigonometry in a nutshell. If we know an angle and one length of a right triangle, we can pretty much figure out all the other components of that right triangle. The first thing we need to find our trail calculation is the length of the triangle along the ground, point O to point S. We know the rake angle either by measuring it or getting it from the manufacturer's specifications. The most accurate way to determine the rake angle is to measure it directly, because the manufacturer's specs assume that the bottom frame rails are perfectly parallel to the ground. But variables like the length of the forks and the size of the front wheel could make it so that those frame rails aren't parallel. Getting the height of steering head H is as easy as measuring it with a tape measure. And once you know the angle R, you can find L by using the tangent function, since L equals H times the tangent of R. We also need to know the distance from point O to point W, and we can measure that directly using a plumb bob and a tape measure. We'll call this length lowercase l, which is useful for finding the distance between S and W. Now, it's tempting to either measure or calculate this distance here and call it the trail. But industry professionals refer to that length as the false trail. Remember that torque is a measure of force times distance from an axis, and the distance to that axis needs to be measured at a perpendicular angle. What we actually need to find is this length here, the perpendicular distance from point W to the steering head axis. This distance between S and W is just the hypotenuse of another right triangle. If we take the sine of angle G and multiply it by that hypotenuse, we get the bike's true trail, which is exactly what we're after. So how much trail do we want? Unfortunately, if you like to do research on the internet, this is one of those questions you can ask 100 different times and get 100 different answers. I saw one website where a gentleman said he likes to have his trail right around 1.5 inches because that's the trail setup he had on the superbikes he used to race professionally back in the 80s. I wouldn't go near a bike with only 1.5 inches of trail. Maybe 40 years ago, on a race bike with specialty designed suspension components, it made sense. But on a modern bike used for street purposes, it's way too little of a trail figure. On the other hand, I also saw a post about a chopper with about 10 inches of trail. And with that much leverage between the road and the wheel, you're not going to turn those handlebars unless you've got forearms like Popeye. So in the absence of a conventionally accepted figure, I turn to the industry giants to see what they're doing. Typical sport bikes by Honda, Kawasaki, and Yamaha have advertised trails of 3.8 to 4.0 inches. Harley Sportsters and Dynas have trails in the range of 4.3 to 5.0 inches, and heavier Harleys like Softails run trails anywhere from 5.2 to 5.8 inches. Now, Harley touring bikes are a special case that I want to highlight here because the engineers that designed the touring chassis really did their homework. The entering argument is that touring bikes are heavier than the other bikes in the Harley lineup, and the intention was to make them easy to handle during slow-speed maneuvers, like in a parking lot, without sacrificing high-speed stability, like during travel down the freeway. Harley does this with relatively conservative rake angles, typically between 26 and 29 degrees on most of their touring bikes, compared to the 32 to 36 degrees most of their softails use. That tight rake angle tends to make for a shorter wheelbase and a more responsive front end. But a bike that heavy needs some extra help maintaining stability, and Harley achieves that with extra large trail figures. If you've ever seen a touring triple tree up close, you'll notice that it's backwards compared to the other triple trees Harley uses. That backwards triple tree positions the wheel for a trail figure of 6.4 to 6.9 inches, making for the best of both worlds. The steep rake angle allows for quick handling characteristics, and the backwards triple tree moves the front wheel further away from the steering head axis, giving the bike the extra long trail that it needs. So the combination of steep rake and long trail effectively negate the extra weight of such a heavy bike, and you have to respect the amount of ingenuity that went into making that happen. All this to say, I assess that trail figures between 3.5 and 6.5 inches are acceptable. The larger and heavier your bike, the more trail you're going to want, but 3.5 to 6.5 inches seems to define the industry standard for most bikes, and that's what I'm going to use for my analysis on Black Velvet. Now, I need to measure the rake angle on the bike, and the first order of business is going to be calibrating my electronic protractor. I'm going to assume the floor of my garage is flat enough to be considered 0 degrees, and I'm going to calibrate the protractor by placing it on the floor and zeroing it out. Now remember that rake is measured from the vertical, not the horizontal, so while it's both convenient and accurate to calibrate the protractor against the floor, that's not going to give me the rake angle when I put it on the frame. It's actually going to give me the complementary angle, and my actual rake angle is going to be 90 degrees minus that figure. But once I get my rake angle, the rest should fall into place. So let's take some measurements, do some math, and see if this thing's going to ride like a caddy, or see if I built a death trap. So the calculated trail is just less than 5.2 inches, which is right in the middle of that acceptable range. For that matter, it might be slightly on the high side for a bike that weighs practically nothing, but that just means it's going to handle really well in the straightaways. And I'm not concerned about how it's going to handle the corners since it is so lightweight and the wheelbase is so short. Now, remember earlier in the video, we talked about raked triple trees, and you might be asking the question, are they a good thing or a bad thing? Here's a comparison of standard trees and raked triple trees with longer forks on the same frame. If you're looking for a quick and dirty way to extend the front end on your factory bike to get that chopper stance, but you don't want to cut, stretch, and re-weld the frame, you might be tempted to use raked triple trees. But what you need to know is that you're moving the front wheel forward without changing the position of point S. Effectively, you're reducing the trail, and not only will you void the warranty, but you could also create a front end with a dangerous tendency to wobble. So is there a good use for raked triple trees? Absolutely there is. See, the larger the rake, the larger the trail tends to be. And on choppers with more extreme rakes, like 40 plus degrees, the front wheel naturally sits in a position that creates a trail figure that's too large. So reducing the trail with a set of raked trees will actually help the bike handle better in a situation like that. I have a CFL that I built a number of years ago with 4 inches of upward stretch, 38 degrees of rake in the frame, 3 degrees of rake in the triple trees, and 6-inch overstock front forks. The end result is a bike with a total rake of 41 degrees, frame rails that sit perfectly parallel with the ground, and a trail figure of just over 5.0 inches. So raked triple trees absolutely have a place in the motorcycle industry, and now you're armed with the knowledge to decide if it's right for you. Thanks for watching. Like, comment, subscribe, and if you haven't gotten your hands dirty in the garage today, what are you waiting for? Ride safe.